Well, greetings and welcome to this short introduction to what I will call the foundational idea in all of electrostatics. It's known as Coulomb's law of electrostatic forces, and you'll notice as it's being described here a similarity to Newton's law of universal gravitation, which you probably have already studied if you're in a typical course in electromagnetics, because you probably already studied mechanics. So just to remind you, Newton's law of universal gravitation states that all masses are attracted to each other with a force that is proportional to the amount of mass in each object and inversely proportional to the square of the separation distance between the centers of the two masses. And we have the gravitational constant that we use for that, very tiny little constant, 6.67 times 10 to the minus 11. That's how many newtons attract each kilogram if they are placed 1 meter away from each other. Well, Coulomb's law for electrostatics describes not just an attraction, but possibly a repulsion. And over here on the right, you'll see that we could have opposite charges, a positive and a negative. That could be fundamental charges like a proton and an electron, or it could be larger objects that have acquired some charge due to charging somehow, maybe by friction or by induction or by conduction. But however it gets charged, we could have a net positive charge on one and a net negative charge on the other. And then there is a force of attraction between them. Notice this is an interaction pair. So this is not just a force of one object on the other, but an interaction between the two. You cannot have the negative charge pulling on the right one without the right positive charge also pulling on the left one. The repulsion works in exactly the same way. It's got to be an interaction, which means that if the left negative charge is repelled, then the right negative charge is repelled just as much. They don't even have to have identical charges on them. Kind of looks in this figure like we have just as much charge on one as we have on the other. But it makes no difference whether one is charged a lot and one just a little, or whether they're charged equally. They still must have identical forces of attraction or repulsion. Now, when you calculate the amount of force, you're going to use what's called Coulomb's law, which is here on the right. And we can write it this way. This is probably the easiest form. And notice that same form that I said you saw in universal gravitation law, except that instead of masses being the critical factor, it's the amount of charge. We use the symbol Q to denote how much positive or negative charge is acquired on each object. And that would be measured in units called coulombs. And then in the denominator, you'll see the square of the separation distance. We call it R, or sometimes you'll see it marked as a D, or lots of other different symbols could be used for that separation. And so that gets squared. And then we have the fundamental constant for electrostatics here, noted as K. K is actually one of the easier constants for me to remember, maybe because I use it so much, but it's 9 times 10 to the 9th when you round it to 2 digits. So 9E9 on the calculator works very nicely, and that's units Newton meter squared per Coulomb squared, just like the universal gravitation constant was Newton meter squared per kilogram squared. So just have to get used to using these new Newton units for charge, which are in coulombs. Now, later in a course, you're often going to find it more convenient to write Coulomb's law this way. There's really nothing different here except in how we write the electrostatic constant. That K can also be written as 1 over 4 pi epsilon sub naught. That's the Greek letter epsilon. Looks like a little script-looking E with a subscript of 0. We call it epsilon sub naught. And it has the value of 8.85 times 10 to the minus 12. And its units are the inverse of the units for K, so Coulomb squared per Newton meter squared. And if you put that in and put 1 over 4 pi times that number and then invert it, or I'm sorry, not invert it, but 1 over 4 pi epsilon sub naught, you will indeed get 9 times 10 to the 9th. So you might be thinking, well, why would I put a big fractional unit in there with kind of a weird looking epsilon sub naught? And I don't know that the answer to that is obvious now, but later when we start getting into some spherical symmetry and using this expression to do other things, you're going to see that some things cancel out nicely, and you're going to end up wanting to use that stranger looking form. So this again is the foundational law for all of electrostatics, and again hard to see now as you just start your introduction into it, but it's going to drive everything we do from our study of energy as it relates to electrostatics to how electrons actually move through circuits. We start building circuits and lighting up light bulbs, and eventually this is also going to interplay with magnetism. But don't want to get too far ahead of ourselves here. We're just in the foundational step. So hopefully that was a little helpful introduction, and you can make some headway on whatever your next step is.